Hello, we are going to go over today how to work on combination problems that have energy involved. When we are given a problem that looks big and daunting, we should read through the problem and start to identify what topics are happening. We should draw pictures of the object at the different locations, and then we should start trying to use our tools to solve. So this problem says, number one, what is the maximum height h the ride can start from rest and just barely stay on the track at location 2? So let's go into this problem and kind of see that we're looking for the maximum height h right here. This is what we want to find. So that the cart just barely stays on the track at location 2. Location 2 here is at the top of a circle. And so we could start noticing things like what the height is at location 2. It's not just one radius r, but 2. So we could say like that the height at 2 is equal to 2r. And so we want to know if we start from rest at the beginning, right here, v equals 0, to just barely stay on the track. Why would we go off the track? Well, when we're going in a circle, we would go flying off the track if we're at a speed bigger than the critical speed. So we're trying to notice here that this problem is reminding us of circular motion. To just barely stay on the track, we're going to say like, hey, could this be a critical speed problem? Could this be a problem where the force of gravity is the net force pointing towards the center? And it turns out that yes, at location 2, the force of gravity is pointing towards the center of the circle. And so to just barely stay on the track really means for your normal force to go to 0 for just a second. And so we notice that there's some circular motion happening here. And so we recognize again that the critical speed follows that equation, square root of rg. And we think, okay, this is just a circular motion problem. But when they say what's the height that you need at location 1 in order to have a speed at location 2, now all of a sudden I'm starting to think like this is probably an energy problem as well. That as I'm looking at two different locations, location 1, location 2, object 1 and object 2, I want to try to draw myself an energy bar chart here and say like what's happening. At the beginning, I'm at rest, so my kinetic energy is 0. But I do have a lot of height. So I have some gravitational energy at the beginning. And I want to say that that energy is energy that the cart and the earth share. And then at the end, I'm going to say that I do have height above the ground, just less height. I don't know if it's half the height or whatever, it's just less height. And then whatever I've lost in gravitational energy, it had to go somewhere. And I'm going to say I made up for it in kinetic. Because they didn't say there was any friction. They didn't say that there was any sound. I'm going to go ahead and assume that the energy at location 1 has to be equal to the energy at location 2. I'm going to go ahead here and say that the total energy, all of them combined, this plus this, has to equal all the energy at the end, that plus that. So this is energy at location 1. This is energy at location 2. So when I notice it's an energy problem, I recognize I can get a point for just saying energy at 1 equals energy at 2. And I can get points for just recognizing what types of energy. I can say, oh, there's gravitational energy. So I'm going to write the equation for that, mg delta y. There's kinetic energy. I'm going to write the equation for that, 1/2 mv squared. And now I have to put it all together. I have to say, hey, all that energy at 1 is equal to all that energy at 2. And I can start getting, a little specific about that by saying like, hey, let's write what is happening at 1. At 1, it's all my gravitational energy at 1. And at 2, I have gravitational energy at 2 and kinetic energy at 2. Then I can say that gravitational energy at 1 would be mgh. H is what they call the height at location 1. At location 2, I'm going to say that that's mg. I'm not going to call it h. I'm going to use the fact that that's 2r above the ground. So the height of a circle is oftentimes found by doing twice the radius. And then there's also kinetic energy, 1/2 mv squared. And so again, my goal is to isolate this height right here. I'm trying to solve for the height I need in order to be at a very specific speed. So this is the link here between the two worlds, is that the speed that I'm going at is this critical speed. So if I'm going at the critical speed, I can now plug that speed in right here. And so I can get an expression for my height in terms of this, the square root of RG. So as I kind of zoom in here, I'm going to put the square root of RG in as my V. But you know how that is squared. And then I'm also going to do 1/2 m plus, I'm going to pull the 2 out front, 2 mgr equals mgh. And then I need to isolate h. So as I am trying to isolate h, you will see that I need to divide both sides by mg. But before I do that, I could probably consolidate things a little bit. Like for instance, the square root of rg squared is just rg. So I have 1/2 mrg plus 2 mrg. It's going to give me 2.5. 2.5 mrg is equal to mgh. Now, as I am trying to solve for my h, I'm going to divide both sides by mg. And I get that the height that I need to start from is equal to 2.5 r, the radius of the circle. And that height starting will turn out so that my speed at the top of that loop is the critical speed. And so that is how you put together your circular motion of critical speed with your energy equations in order to merge into a combo problem. Now, this problem continues to say if the car did start from rest at location 1, what would the delta x be of the spring in order to stop the car? So now when we're looking at this is still an energy problem, but we have different places to isolate here. We're going to say, hey, I started at location 1, but I'm going to end over here at location 3. So as I am comparing location 1 to location 3, I'm going to say that at 1, all of my energy is gravitational. Bella says hi. Because I'm not moving, there's no kinetic, and that's the cart and the earth that are sharing that energy. But at location 3, I've stopped, so there's no kinetic. I'm at the ground, so there's no gravitational. But I'm compressing a spring now. So all my energy becomes stored in the spring. And so now the spring is what's storing the energy. So for this part, I can again say that my energy at location 1 is now equal to my energy at location 3. There's no outside forces doing work to make the energy transfer. So then I can say that the gravitational energy at 1 all turns into spring energy at location 3. And I should write the equation for spring energy all by itself, just in case I did something else wrong here, because you know that's going to be a point. I've already written my equation for gravitational energy from before, but it doesn't hurt to just do it again here. And now I'm going to plug in like the specific variable. So this is mgh, turns into 1/2 delta x squared. This time the mass does not cancel out. And so to solve for this delta x, I'm going to first multiply both sides by 2. So I'll get 2gh k delta x squared. I'll divide both sides by k. I get delta x squared equals 2gh over k. And last but not least, we have to take the square root. So the amount that the spring will be compressed is going to be equal to 2gh over k. And so, again, being able to identify where am I using energy? What are the places I care about? Why didn't I set location 2 equal to location 3? I could have, and I would have actually gotten the same answer. But location 2 is messier. I have kinetic, I have gravitational. And you know what? The energy is the same from 1 to 2 to 3. And so I'm able to say, hey, since there was no work done, I can take my energy at any place and set it equal to my energy at any other place. And so this is how we kind of review the different types of energy, a little bit of circular motion, how to break problems apart and put them back together again. And so have a great day.